Okay, physics. So we've been taking a shortcut for a little while. That's pretty handy, but yeah, let's learn about how not to do it with the shortcut. So here's the shortcut that we've been taking. We've been saying, here's something, and there's a force acting on that, and that force of gravity we're going to call mg, right? Shortcut. So it turns out, right, that this is what we do on the surface of the Earth. But as you get further away or even inside the Earth, that then things change. So it was Newton who figured this out. So this is the universal law of gravitation. And he said, well, if there are two masses, that they'll be attracted to each other. So it kind of looks like this. So if I have two masses, it doesn't matter where they are, what they're doing, that if I have two masses, that they will be attracted to each other. And notice that these are paired forces again. So I'm going to have forces that show up in pairs. So these are equal and opposite. Importantly, that no matter what the size difference is, the forces are going to be equal. Now think about this. So the Earth is attracting you to itself, and you're also attracting the Earth to yourself by an equal amount. It's just the Earth is really huge. And we see some effects of this, right? So the Earth is much larger than the Moon, but the tides are partially due to the effect of the gravitational pull of the Moon on the Earth. So we're both attracted to each other. The Earth orbits around so the Moon orbits around the Earth because of the gravitational attraction between the two, and the Moon also affects the Earth. So importantly, these are there's pairs of forces. So again, the couple of key points that the force of attraction between two masses is going to be directly in line between the two. So those two masses will be those two forces will be directed directly towards each other. And we're going to have a formula for this, of course, it's physics. So Newton was the one that figured this out. And here's the formula. So the formula says that the force of any two objects, so the force of attraction between any two masses, is this function of some constant g times the product of the two masses divided by the square of the distance between them. So it took a while. Cavendish, 100 plus years later, figured out what the value of g was. So Newton didn't have sensitive enough equipment. Figured out, Cavendish came up with a really nice experiment to describe that. And it turns out g is really small. So g is really small because gravitational attraction is not that great, right? So you're actually attracted to everything that's around you. So the screen that you're watching this on is attracted to your body, but it's so small that it's inconsequential. So gravity is the weakest of all the forces. So the four fundamental forces: strong nuclear, weak nuclear, gravitation. So gravitation is the weakest of those, and the strongest of those that act at a long distance is electrical. So we'll get into those later. But let's play around with this a little bit. So let's see what we can do. So we go here. So this is mg. So again, Newton's universal law of gravitation said I can calculate the force of gravity as being some constant g times the product of those two masses divided by the square of the distance between those two. So if we have something that, and this is the shortcut that we've taken. So so if we say, well, my force of gravity is mg, so I have something that weighs, I don't know, 10 kilograms. I could plug this in, right? So I can say, well, what's my force of gravity acting on that in the surface of the Earth? Well, that's going to be my 10 kilograms times 9.8, and that's going to give me 98 newtons of force. Well, let's go the long way about it, right? So it turns out for a sphere that I can, here on the surface of the Earth, right, we're more attracted to some material close, but the other stuff is further away. On average, though, we can use the center of the mass as mathematically equivalent to having all the mass distributed. So technically, from you to the average position of all the mass of the Earth, that's to the center of the Earth. So let's see. So my radius between you and the center of the Earth, let's see, radius of Earth is 6.368 times 10 to the 6 meters. What's my mass? The mass of the Earth, it turns out, is 5.972 times 10 to the 24. 24, yep, kilograms. And again, my constant g is going to be, what's my g going to be? 6.637. times 10 to the minus 11. I'm thinking Planck's constant, 6.67 times 10 to the minus 11. And to make this work, we're going to give it some newtons, some units, which are newtons, meters squared per kilogram squared. It just makes it work out, so I end up with force in the newtons, right? Convince yourself that makes sense. My kilograms have to cancel and my meters have to cancel. Well, let's do a little bit of math, right? So I'm going to take these things and plug it in and see what we get, right? So my force of gravity is going to be G, 6.67 times 10 to the minus 11, times my mass here, so 10, times the mass of the Earth, which is 5.972, times 10 to the 24. I'm going to divide this by 6.368 times 10 to the 6th, and I'm going to square that. Whew! It's a lot of typing in your calculator, but if you do this, you know what you get? You get 98 newtons. Right? Give it a try. Convince yourself that that's true. So what does this tell us, right? So we take a shortcut. So our G is telling us, we can think of it telling us as the acceleration, which is true. It's the acceleration something we'll experience. But it also is telling us the strength of the gravitational field. Now think about this, right? So all around the Earth are going to be these gravitational fields. And as you're closer to Earth or further away from Earth, if you place a mass there, it's going to generate some force, or it's going to experience some acceleration. So as you get further away, these smaller arrows, right? So you're going to have less of a gravitational attraction. So what does this mean? Well, we have two ways of thinking about this. So our value of G is telling us two things. It's telling us acceleration that an object will experience when it's close to Earth, and is also telling us the field strength. So it's telling us how strong the gravitational attraction is at that point. And if you think about this, right? So what are we doing? So we're taking our force of gravity, G m1 m2 over r squared, right? So right, m1 is the same. So all of the rest of this is really representing our gravitational field. Or I can think about this as the force of gravity per mass is going to be G mass of the Earth in this case divided by the radius of the Earth in this case squared, and that's going to be equal to what we call G. So importantly, this is telling us two things. It's telling us our gravitational field strength, and it's telling us the acceleration, or you can think of it as the force you experience per mass. And we're going to do something similar when we get to electricity, and we'll have electrical charges that we'll think about the same thing. And we'll come back to this a little bit more when we get into Kepler's laws of planetary motion, probably after we get into rotation and angular momentum, because it's a convenient time to go into his laws at that point. But we have two ways that we can determine the force of gravity. Here on Earth, we have a shortcut, and we have a longer way of calculating that. Hope that's helpful. Talk to you soon. Bye.